The point about subdivision is supposed to be to reduce the size of simplices. So our next task is to quantify that and give an exact measure of what we mean by the size of simplices and prove that subdivision reduces it. So for that, we basically, kind of main ingredient, we need a measure of what's the distance between points in Rn. And of course, there is different versions of the distance in Rn. It turns out the most convenient one to use for our present purposes is the L1 norm. So that's the norm of a vector x is just the sum of the absolute values of the entries in x. Okay. And so the distance from x to y we're going to take as the L1 norm of x minus y. Okay, so now we've got some abstract simplicial complex K, and suppose we've got some map F from the realization of K to some Euclidean space Rn. It's supposed to be a map that's affine on each simplex. So if you've got a point x is sigma xi vi, then f of x is sigma xi f of vi. So then we're going to define the mesh of F to be the maximum of the L1 lengths of the edges. Okay, so the images of the edges under F. So for every edge A, B and K, we take f of A and f of B. Those are going to be points in Rn. We take the L1 distance between them, take the maximum over all possible edges. So that's the length of the longest edge in the image of the realization under F. And notice this can also be written in a slightly different way, and we look at all points u and v, which both lie in the same simplex sigma, and we take f of u minus f of v and the L1 norm of that. So I'm going to claim that the maximum of those values is exactly the same as the mesh. I mean, that's just the same as saying, like, you've got some affine simplex in Rn, and you want to look at what's the maximum possible distance between any 2 points in that simplex. Well, what you have to do is you just take the longest edge and distance between the ends of the longest edge. That's the maximum possible value of the distance between any 2 points in the simplex. That should be geometrically reasonably clear. We'll leave a formal proof to the reader. So yeah, here's just a picture right here. Here's a we've got some abstract simplicial complex K, and which has got these kind of 8 two simplices, and this picture shows an embedding of the realization of K in the plane R2. And the mesh for that embedding is just going to be the length of the longest possible edge, and all of these 4 outer edges have the same length, and so we just take the L1 length of the vector b minus a. That'll be the mesh for this map F. So that's what we get for this particular picture here. But there is a kind of a most obvious sort of type of embedding that we could think of. We just we've got n vertices a1 up to an for our simplicial complex K. Then we can do the sort of affine embedding where we just send ai to the ith basis vector in Rn. So if we wanted to do that with this picture that we've got here, then we would have to, we've got 8 vertices, so we'd have to have an embedding in R to the 8, which we can't really draw. So we prefer to draw it in sort of in dimension 2, like we've got here. But if we did do this kind of very inefficient embedding where we just send each vertex ai to the basis vector ei, then the mesh of that is just going to be 2, right? Any edge, you've got from ai to aj, say, then you've got f of ai is one basis vector ei, f of aj is a different basis vector ej, and then so you're looking at ei minus ej. It's a vector whose entries are mostly 0, and then there's a +1 and a -1, and you take the L1 norm of that, you're going to get 2. So the mesh of that is always going to be equal to 2, except in the trivial case where there are no edges, which is you just have a discrete set of points that would have mesh 0, but almost always the mesh is 2. So here's our proposition about subdivision. You've got some complex K of dimension less than or equal to d, say, and we've got some affine map, map f from from the realization of k to Rn that's affine on each simplex, then you can compose that with our subdivision map beta, and f composed with beta, that's going to be a map from realization of k prime to Rn. Again, it's going to be affine on each simplex. The claim is the mesh of f composed with beta is less than or equal to d over d plus 1 times the mesh of f. So the key point here is this is some factor. Doesn't depend on the precise details of the complex except on the dimension, and it is strictly less than 1. It's not that much less than 1. I mean, this is if you've got a very high dimensional complex, then the shrinking factor is quite is pretty close to 1. If you've got a 10-dimensional complex or 9-dimensional complex, then you're only shrinking the distance by a factor of 0.9, but you are at least shrinking it by some constant factor less than 1. Okay. So let's prove this. Okay, so R is going to be the mesh of f, and we need to prove that the mesh of f composed with beta is less than or equal to Rd over d plus 1. Okay. So let's think about an edge of k prime. So that's an edge from Tor hat to sigma hat for some simplices Tor and sigma, where Tor has to be contained in sigma. So we can write the vertices like this. So Tor is v0 up to vp, and sigma is v0 up to vq. So on p and q, so p is going to be less than q. So that means that the vertices of Tor are just the first p vertices of sigma. And of course, because the dimension is at most d, that means that this q here has to be at most d. Okay, so then we've got these vectors ai as f of vi, and by the mesh of f is at most r, so that means that the L1 norm of ai minus aj has to be less than or equal to r for all I and j. So let's look at what f does to this, what f composed with beta does to this edge Tor hat sigma hat. So we look f composed with beta applied to sigma hat. Okay, so that's sigma hat, remember, is v0 up to vq added together and divided by q plus 1. Apply f to that, we get 1 over q plus 1 times the sum of the aj's, j running from 0 to q. And it's going to be convenient to sort of rewrite that slightly. Okay, so here we take the sum from I as 0 to p, j as 0 to q of aj, right? So this doesn't really depend on p, or on I, so we're really just doing the same thing p plus 1 times, so it gives us an extra factor of p plus 1, but we're dividing by p plus 1 here, which cancels that out. So this thing is the same as that thing. And let's think now about f of beta of Tor hat. Okay, so Tor had v0 up to vp, so Tor hat is v0 plus up to vp all divided by p plus 1. We apply f to that, you get the sum of the ai's from I as 0 to p divided by p plus 1. And again, we can rewrite that. We can have a sort of kind of irrelevant sum over j here, j running from 0 to p. Q doesn't really depend on j, so this is just q plus 1 times the original sum, but then we've put in an extra factor q plus 1 inverse on the outside to kind of cancel that out. And so this sum here is the same as this one. Okay, so now let's look at the difference between these two things, right? We're supposed to be looking at the distance between these 2 points. So we take the difference between the two vectors. Okay, so we've got the same we've got sums indexed in the same way. You've got the same factor p plus 1 inverse q plus 1 inverse on the outside, and on the inside we're just taking the difference aj minus ai. So now we have the triangle inequality says that if we take the norm of this difference here, then that's going to be less than or equal to the sum of the norms of all the terms. So you've got p plus 1 inverse q plus 1 inverse times this sum here of aj minus ai, the one norm of that. Okay, so that's what we've got. It's the length that we're interested in, less than or equal to 1 over p plus 1 q plus 1 times the sum from I as 0 to p, sum is j as 0 to q of the one norm of aj minus ai. So let's think about this. Here, the number of terms, this is p plus 1 terms from this and q plus 1 terms from that, so that's p plus 1 times q plus 1 is the total number of terms in this sum. However, some of them are 0. Right? Okay, if we look at the case where I is equal to j, remember here that p was less than or equal to q, so we can only have I equal j in the case when I is less than 0, I is running from 0 to p. But in those cases, you've got ai minus ai, and that's just 0, and we drop out that term. Okay, so that's p plus 1 terms we can get rid of. So we had p plus 1 times q plus 1 terms before, and we've got rid of p plus 1 of them. So that leaves p plus 1 times q terms, which are non-zero. And each of those terms is less than or equal to r. That's because r was the mesh, and each of these aj minus ai, each of these terms, it's the length of some edge, so it's less than or equal to r. So we've got here, we've got this factor p plus 1 inverse q plus 1 inverse from the outside. Then we've got p plus 1 times q terms, and each term is less than or equal to r, so we get this inequality here. But then here we've got some cancellation. This p plus 1 inverse is cancelling with that p plus 1. So we've got this qr over q plus 1. And remember here, q is less than or equal to the dimension d. So that means that q plus 1 is less than or equal to d plus 1. Then we take 1 over it. The inequality flips over. So 1 over q plus 1 is greater than or equal to 1 over d plus 1. And then we take 1 minus it. That flips the inequality back again. So q over q plus 1, that's 1 minus 1 over q plus 1, less than or equal to 1 minus 1 over d plus 1, which is d over d plus 1. Okay, so here this q over q plus 1 factor here is less than or equal to d over d plus 1. So what we're seeing is that this length of this vector here is less than or equal to dr over d plus 1. Okay, and that was true for every edge sigma hat tor hat. So seeing that the mesh of this map is less than or equal to d times r over d plus 1, which is what we claimed. So we're shrinking the mesh by this factor d over d plus 1.